Okay, so we can collect and organize our historical data from many different sources into a data warehouse. But now that begs the question, how do we organize that data in the data warehouse? So here's an example of sales data. So we have a big table here that has the product name, the category, the price, the quantity, and a date of a sale, the day of the week, the city, the state, and the county or the country rather, where the sale occurred. So what we've created here is a big table with many columns representing different aspects of a particular sale and many rows where each row is a particular sale. So there's a lot of redundancy here. And so storing all of this data is going to be expensive. And accessing the data is also going to be expensive because it's going to take up a lot of space on a disk, which means it's going to take a lot of time to read all of that data just to look at what was the price that we sold corn for in Omaha on March 31st, 2016. So the other issue is that we might make mistakes when we're updating this table. So what happens if someone misspells Omaha or doesn't know that Omaha is in Nebraska and puts down Iowa instead for the state? So is there a way that we could more efficiently organize the data that's in this table? So if we look at this table, we can see that there's a lot of redundancy. For example, the city, state, and country are always the same, in this first set of rows, right? So if we have lots of sales that are occurring in Omaha, Nebraska in the US, why do we have to list Omaha, Nebraska in the US many times, right? Similarly, maybe we have lots of sales of peanuts in Seoul, Korea. So do we need to list Seoul, Korea, Seoul, Korea, Seoul, Korea every time we have a sale in Seoul, Korea? So instead of thinking about this as independent rows, we can think about the relationships between the rows and realize that there are actually multiple dimensions here to this data. So a multiple dimensional data model would look like the following. We have a fact table that tells us that we had a particular product that was sold at a particular time, at a particular location, and for a particular price. And then we have additional tables, dimension tables, that tell us the information about what's in the fact table. So for example, that location ID references a location. So that first row has a location ID of 1, and if we look in our locations table, we can see that that's Omaha, Nebraska in the United States. Similarly, products, the product ID references the products dimension table. So here, a product ID of 11 references corn, which is categorized as a food and had a price of 25. And similarly, time is also a table, a dimension table in this case, and we can reference it from our fact table. So time ID 1 is March 30th, 2016, which was a Wednesday. Okay, so now what we can do is we can think of our data as a multi-dimensional cube of data. So we have one dimension, which is the location. We have another dimension, which is the product. And we have another dimension, which is the time. And you can really think of this much broader as a hypercube if we have many more dimensions, which in practice, your multi-dimensional table, you're going to have many, many more dimension tables. Okay, so if we think about this, our fact table is minimizing the redundant information. All of that redundant information gets pushed out into the dimension tables. And so it's going to reduce data errors. We don't have to worry about someone mistyping corn as C-R-O-N instead of C-O-R-N. At the same time, each of these dimensions is much easier to manage and summarize, right? We can see, we have sales in Omaha, Seoul, and Richmond, right? And we can see, we have 3 different products that we're selling: corn, Galaxy One, and peanuts. And one of those is a phone, and the other 2 are food. But it also makes it easier. What if we say, the Galaxy One, it wasn't really a phone, rather it was a phablet. So we can very quickly change Galaxy One to phablet, and now all of our references from our fact table to the Galaxy One become references to phablets instead of phones. So in our previous table, we would have had to go through that table and manually change all instances where we saw the sale was for a Galaxy 1 to make it be a phablet instead of a phone. So very efficient and very easy to manage. We also have a normalized representation here. We don't have to worry about someone, what do they do when they try to enter Seoul and there's no state associated with it. We don't have to worry about that. We've decided ahead of time with our dimension tables how we're going to represent each of the facts that appears in each of the components of the fact that appears in our fact table. So now, how are we going to do analysis when we have tables like this? Well, we'd have to do joins, right? We'll have to join together, say our fact table, our sales table, our locations, our products, and our time, and we can regenerate that table that we saw in the previous slide. The difference is we only need to regenerate a portion of that table. We don't need to regenerate the entire table. So processing it'll be much more efficient and faster. So now if we look at the schema that we end up with here, we end up with a schema that looks like a star, right? And in this case, it's like a three-pointed star, right? One of the points is products, another is time, and another is location. So I can just abstract that away and it looks like something like this. Now, this is also a star, and this is more likely what you'll run into where there are many dimensions associated with it. And in fact, in a multinational company or a company with subsidiaries, what you might find is that those dimension tables themselves are actually fact tables. And those fact tables have their own dimension tables. And so you don't really have a star, but you really have something that looks much more like a snowflake instead. Okay. So if you want to know a lot more about snowflake and star schemas, take Computer Science 186. All right, now, to actually work with the data, we do something called OLAP, Online Analytics Processing. And this is where users are interacting with that multidimensional data. So there are two approaches that you can take. One is that you just write the SQL queries yourself. They're going to be very ad hoc if you do that. They're going to be very complex. If you can do that, you will be the person in the office that everybody turns to do all of the processing of the data. But it's ad hoc, it's very complex, and that means it's more likely to be error prone. It also requires you to have a very deep understanding of the schema and organization of the data. So instead, what a lot of people use is graphical tools that help them construct the queries. So an example would be Tableau. And this really gets into reporting and business intelligence. Most people, when they're interacting with this kind of historical data, they don't use SQL. Instead, they use these high-level tools to generate slices of the data across the different dimensions. And automatically, under the covers, it's generating lots and lots of SQL queries, but they're much more likely to be correct than the ad hoc complex queries that you might try to write yourself. And these queries can get very large. The good news is that databases are pretty good at optimizing large queries, but it can lead to very long run times when you're trying to generate some of these visualizations.